ॐ सहनाववतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै ॐ शान्ति शान्ति शान्तिः।
The last class we were inquiring about a quantity called stress. We said that stress is the result of forces. Remember that we said the forces can be classified into what are called as surface forces and body forces. Okay, that is where we stopped. We started defining what is stress. What was the difficulty we had? We said that stress in our earlier classes rather, that stress is nothing but force per unit area. Okay, we divided this or normalized the force by area and it was very simple. But when the body takes the shape of a very complicated connecting rod or something else like what we saw in many of our examples, or for example the sheet of the sidewall of a coach and so on, then it may not be very easy for us to define or to use this simple formula. It is okay as far as a bar is concerned. As far as the bar is concerned, I apply a load like this, then yes, it is quite simple to state that the stress can be defined as force per unit area, or sigma is equal to F by A. But the problems, or the real life problems rather, are not as simple as this. So we have to have a much more rigorous understanding of stress. Let us see the definition of a stress from a more rigorous three-dimensional setting. Now let us consider a body. Let us put some coordinate system for it. Let us call this as say x1, x2 and x3, and let us say that there are forces that are acting on this body, and that there are some what are called as boundary conditions. Remember, we had already talked about the importance of the boundary conditions in one of our earlier classes. Now let us take this body out and let us cut this body by an imaginary plane. Okay, our interest is to define a stress at say a point P. Is that clear? Why is that we are interested in a point P? Remember, when you saw our results, you saw a lot of colors there. So in other words, stresses was defined throughout the volume of the body. Hence, we have to define stress at each and every point of the body. Is that clear? So let me take a point P and let me cut the body with a plane which passes through this point P. Let us say that the normal of this plane is equal to n. All of you know that n is of course a vector. Okay, that is the normal. Let me now keep these two bodies separately, forget for a moment all these forces and the boundary conditions, and let us consider the two bodies separately. My point is P is here. Let us say that we take an area around this point P and call this as say ds, right. Remember that the normal at this point is n. Is that clear? The normal at this point is equal to n. It is obvious that if I call this as say one part of the body and the other as the second part of the body, then there is an influence of the second part of the body onto the first part of the body. The influence is through a force. Let us say that the influence at this point P is equal to some F, or if you want you can say delta F. Okay, that is a force that is acting. Is that clear? Okay. Now let us stick to our old definition of stress, but the only difference now is that we are going to talk about area which are around a point P, or in other words, let us now say that the average of these forces that act at this point P can be given as say delta F by say delta S. Okay. For a moment, to stick to our delta F here, let me call this as delta S as well. In other words, the average force or the average forces due to the influence of the other body at an area surrounding the point P is given by delta F by delta S. Now when I started this problem, I said that let me take a small area around P, and now what I have done is to take an average of delta F by delta S. Now there are two questions that may come to our mind. One is that how small is small, because as I take larger and larger areas, the force distribution may not be very uniform, so I will get different values of this average. Remember, this is force area. The definition is still there, or old definition is still there. So one argument is that if I keep taking different areas around this, because you have not defined how small is small, so I can take one area, then another area, and so on, I may get different values at this place. Is that clear? Because I am averaging out in an area, and especially when the force distribution around this point P, as I cut it and look at the influence of this body onto this body, the force distribution may not be very uniform. If it is uniform, there is no problem. If it is uniform, then delta F by delta S would remain the same. But if it is non-uniform, the average may rise up, go down, or whatever it is. So I have a small problem there. So in order to alleviate that problem, I define a stress as limit as delta S tends to 0, delta F by delta S. This is what I define as a stress, say T. Since I have got this stress by cutting with a plane whose normal is n, I call this as T n with a subscript n. We will come to this in a minute as to why this n becomes important physically and then more mathematically. I will come to that in a minute. But before that, let us look at this quantity. Please note that this quantity is a vector. It is a force, the influence of this body over this at that point, which is of interest to me. In other words, this is a force. Influence comes out as a force. Is that clear? So this quantity is a vector, because this is nothing but an area. So this is a vector. So we call this T with such a definition as stress vector. As a stress vector. Is that clear? If you remember, if I had this particular bar, and in fact if I had cut this piece, if I cut it into two pieces like 1 and 2, if I had asked you to draw a free body diagram for this, you would have drawn in this side something like that, and this side a corresponding force that is acting in the opposite direction. And you would have told me that this is nothing but the internal force which is the result of these stresses. You would have said that this part is sigma A, that part is sigma A, okay? And you would have said that this is under tensile loading. Just extend that here, okay? The only difference now is that as soon as I say what is the stress here, you had immediately a plane in mind which is 90 degrees to the axis of the bar, and you would have taken this plane here. But here what is the stress at this point, then I have to specify the plane. Now physically what does it mean? Physically what does it mean? Let me take, see we have defined a stress at this point as say F by A, where F is the force that is acting and A is the area, okay? And we had actually looked at the equilibrium with respect to the outside and the internal forces. Suppose I had taken a plane like this, what would be the stress with respect to that plane, okay, with respect to this plane? If I had cut a body like that, what would be? It would be 0, right? Or in other words, at this plane the stress would be 0, whereas on this plane the stress would be F by A. Or in other words, physically we know that stress would depend upon the plane, right? How exactly does it depend upon? We will see that in the course of this class, but it's very clear that plane becomes important, and that poses a problem. What is the problem? This definition of stress vector is for a particular plane whose normal is n. So suppose I ask you a question, what is the stress at a point P, at this point P, which can be related to my point in the actual component? Then the question that you will ask me is, what is the plane you are talking about? Okay, going back to this picture here, I had chosen a plane n. The question you will ask is whether you want the stress at this point P along this plane, or along this plane, or along this plane, or along this plane, and so on. Or in other words, this stress at a point P becomes meaningless because that is also wedded to the normal that you can draw, or the plane which you use to cut it into two pieces and look at the interaction at a small area around P. Is that clear? Clear. So infinite number of planes I can cut. So there are infinite number of values of stress that you would talk about, or infinite values of stress vectors that you would start talking about. But that is quite confusing, isn't it? That I can't talk about infinite number of stresses. So what is the remedy? One thing is clear, that the stress depends upon the plane. Another thing is clear, that I can't just talk about stress at a point P, okay? So the solution to this is to talk about what is called as state of stress at a point at P. What is state of stress at a point P? Now from this definition, it is clear that if I am able to define certain planes very nicely, then I can say that state of stress is related to certain well defined planes. Or in other words, what is a plane which is easy to define for you and me? Yeah, so that plane is defined by my coordinate systems. For example, in the same figure, if you want the state of stress at a point P on the same component, okay, we want the state of stress at a point P, then I can define three planes, 1, 2, and another plane perpendicular to the axis of the board, okay, such that their normals of these or in other words the normals of these planes pass through x1, x2 and x3. So these 3 planes are well defined planes, okay, and the first thing I will do is, okay, I know that it is difficult to define it in infinite number of planes. So as a first step, let me define them in these 3 planes. It turns out, as we will see, that these 3 planes are useful, very useful to us, because if I properly define stresses in these 3 planes as I am going to do now, then it is possible to relate these stresses to any other plane that you would define by means of a normal n. Is that clear? If it is possible for me to say what is the stress in these 3 planes, I can derive a formula to say if you give me what is n, then I would tell you what would be the stress in this plane. Right? Is that clear? Okay. Now let us go ahead and define the stresses in these planes. Remember that right now we are talking about stress as a vector. It is stress vector. Okay? It has both magnitude and direction. Right? Okay. Let me take this point P, okay, and then expand what happens in these 3 planes. Let me take that P here and let me draw a plane whose normal is say along x1. Let me call the base vectors along x1, x2 and x3 as e1, e2 and e3. That is x1, x2 and x3 each have base vectors as e1, e2 and e3. If it is not visible, let me write it quite clearly. For x1 we have e1, x2 I have e2 and along x3 I have e3. Note that I put a squiggle here in order to denote that they are vectors. Okay, people put an arrow at the top on its head like this, or in textbooks you would see that this letter will be written as a bold letter. Now it is not easy for me to write a bold letter here, so I am putting a squiggle at the bottom to denote that they are vectors. E1, E2, E3 in your earlier classes, you would have of course been exposed to this. In your earlier classes you would have defined E1, E2, E3 as I, J, K. That is right, I, J and K. Because of certain reasons which will become clear, okay, maybe towards the end of this class, I have defined them as E1, E2 and E3. Is that clear? Okay. Now let me say that the force that is acting on this particular plane, okay, is equal to say delta T. Delta T, what do I put here? E1 and the corresponding stress due to this as T E1. Is that clear? Okay. What is this? This is exactly the same as this. Now here I have taken some plane with a normal n and defined the stress vector. In this case I have taken a plane whose normal coincides with that of E1, okay, along the same direction as E1, right, and then I have defined a stress. Is that clear? Okay. Now I do the same thing with respect to this point, say P, okay, we are considering that point is P. I am doing the same thing, or I am going to do the same thing with respect to the point P with the planes taken the plane taken such that its normal is along x2, in which case I would get one more, please note this is different, one more stress what vector, okay, which I would write as E2. Is that clear? Okay. And lastly, I will take another plane. How do I take another plane? Oh, very good. So the normal with normal in the direction of x3, which I would call as, whose unit vector is called as E3. So I will get one more stress vector which I will call as E3. So I have defined 3 stress vectors. Is that clear? Okay. So as soon as you see a vector, what is that what is that which comes to your mind? You say that this vector can be resolved in 3 directions. Is that clear? So I can resolve this vector in 3 directions, so that I can write this as, how do I write? T1 in the one direction, okay, E1 into, what do I get? Correct, E1, that's it, plus T2 of E1 into E2 plus T3 of E1 into E3. So this vector is resolved in the one direction, 2 direction, 3 direction. Note this very carefully, that this vector has E1 as the plane, okay. So E1 and E1 remains the same, okay, and this 1, 2 and 3 indicates the directions, okay, and E1, E2, E3 are the unit vectors along the 3 x1, x2 and x3. So similarly I can write this as T1 E2 into E1 plus T2 E2 into E2 plus T3 E2 into E3. Is that clear? And you can write the last guy again as T1 E3 into E1 plus T2 E3 into E2 plus T3 E3 into E3. Already I know that you are complaining too much to write. I wantonly wrote this because I know it is, every time you write like this it's going to be difficult, so you would immediately request me to write it in a shorthand, right? I mean, you have to write so many things, it becomes difficult. We will devise a shorthand technique to write such a complicated equation or such a so many numbers, you know, which has so many indices and so on. We will devise a very simple method of writing it in a minute. It is usual or it is customary to write T's, okay, in terms of what is called as sigma, okay, sigma ji with such that j indicates the plane and I indicates the direction. J indicates the plane and I indicates the direction. So, in other words, to understand this, if I put TE1, 1, that is in other words, what is this? Sigma 1 1. Okay. This is sigma 1 2, and this is sigma 1 3, and so on. See, some of the books would define this as sigma ij. A few of them, for example, Kolsky, okay, very famous book on stress waves in solids, he would define this as sigma ij. I is the direction and j is the plane. But it doesn't matter, because you would shortly see that this sigma is symmetric, or ij is equal to ji. Okay? But usually it is the plane and the direction are the ones that are used to define sigma. Is that clear? Yeah? Any questions? Yes. Now the point is that I have now how many quantities? 9 quantities. Okay? 9 quantities to define state of stress at a point. Of course, when I show you sigma ij is equal to sigma ji, then it will reduce to 6 quantities. But as such, you can see that we have 9 quantities. Okay? Is that clear? So, this sigma ij is defined as the state of stress at a point. Okay? So, state of stress at a point is defined by means of sigma ij, and which you can say is a matrix of sigma. Okay? They are nothing but sigma 1 1, sigma 1 2, sigma 1 3, and so on. Clear? Okay. So, these 9 quantities are the crux or the clue to stresses at this point. Please note that we started with stress vector and resolved that stress vector in the 3 directions. Do you remember? That is what we did. The question is then, what is this sigma? Is it a vector? Is this state of stress is defined as a vector, or is it something else? Can you call this as a vector? No, obviously no, because from the vector stress vector quantity only we have come to this. And also, how many quantities are there? 9 quantities. Okay? So, this sigma state of stress is not a vector, but what is called as tensor. To be precise, it is a second order tensor. It is a second order tensor. Let us not right now worry about this word tensor. You need not be too much taken aback by sudden jump in mathematics. I will define tensor if necessary later in the course more precisely, okay, what is tensor and so on. But nevertheless, you should understand that stress can be expressed as a vector or a tensor. Okay? So, you can't say, see for example, you will say certain things like for example, speed. What is speed? When I say speed, it is scalar. So, when you say velocity, you would define this as vector, right? But when you say stress, then you have to be very clear. If I mean state of stress at a point, then it is a second order tensor. Stress can also be expressed as a vector. There is a relationship between the two. We will come to that in a minute. Is it clear so far? Okay. Now, what is this relationship? Why have I defined this state of stress at a point. In order to understand that, let us do a simple derivation and see whether we can utilize this definition in a much better fashion. Is that clear? Okay. We will take back or let me take you to the same point P. Okay. Now, let me see how to determine the stress vector along a normal n at this point P. Okay. In order to do that, let me construct a small tetrahedron with a height h, about this point P. Okay. How am I going to construct a tetrahedron, small tetrahedron at this point P? Okay. Now, let me shift the origin, or rather let me draw the coordinate system, say at that point P. Okay. At that point, that is the point P, and let me draw the plane of interest whose normal is n, okay, at a distance h. At a distance h. So, this perpendicular distance, that perpendicular distance between this point P and this plane is called as h, okay, the height of the tetrahedron. Is that clear? So, the tetrahedron is now made up of, these are the axes. Okay. What are they? They are, say, x1, x2 and x3. So, this tetrahedron is made up of planes which are normal to x1, x2 and x3, okay, as well as the plane of interest whose normal, say, is n, whose normal is equal to n. Is that clear? Okay. Now, let me say that the area of this plane which I have taken to construct this tetrahedron be, say, delta S. The same concept as before. Only thing is I have just shifted it a bit. Yes, I know you have an objection. So, let me say, let me look at the result as h tends towards 0. What is the result? It has h tends towards 0. So, when h tends to 0, this plane, okay, whose normal is n, will pass through the point P, right? Okay. Now, let me say that the three planes whose normals are in the x1, x2 and x3 direction has an area equal to delta S1, delta S2 and delta S3 respectively. In other words, delta S1 is the area of the plane that is formed, that plane whose normal is along x1, and delta S2 is the plane whose normal is in the 2 direction, and delta S3 is the plane whose normal is in the which direction? 3rd direction. Okay. Now, the relationship between delta S1 and delta S, delta S2 and delta S and so on is very clear. Please note that you can define the area also as a vector and call this as delta S is equal to n delta S. So that delta S1 can be defined as n1 delta S. Resolving this in the one direction, I will get delta S1 is equal to n1 delta S. Similarly, delta S2 is equal to n2 delta S. What is n? Please note that it is normal, okay, which results in the direction cosines n1, n2 and n3, right? I am sure, yes, all of you are familiar with this, so I am not going to repeat what it is. So delta S1 is equal to N1 delta S, delta S2 is equal to N2 delta S, and delta S3 obviously equal to N3 delta S. Okay, is it clear? Now please note that these three planes, the N1, N2 and N3 planes, are also planes which I have used to cut the piece. So I have taken this piece out. Actually what is that I have done? I have taken this piece out from the original body. Clear? Now in these planes also forces will be acting, right? The body is to be in equilibrium, so forces will be acting in these three planes as well. Let the force that acts on these three planes be denoted by T1, okay, T say TE1, TE2 and TE3. Is that clear? Is that clear? Okay. Now let us now look at the equilibrium of this body. Let us look at the equilibrium of this body. How do I now look at the equilibrium of this body? What do I mean by equilibrium of this body? I say that what is that I say for equilibrium of the body, or what is the condition that I should apply? Yes, correct. So F sigma of the force vector should be equal to 0. Okay. Now what are the forces that are acting on this body? What is the body that is of interest to me? It is this body. Okay, it is this body that is of interest to me. So this body consists of three planes, okay, and an inclined plane. The forces that are acting in these three planes are TE1, TE2 and TE3. Of course they are vectors, I need not do it every time, plus a force that is acting on this plane, which is say Tn, which is say Tn, okay. Apart from this there can be one other force. What do you think is the other force that can act apart from these three? Yes, they are what we called as body forces. The gravity force is one type of body force, correct. So apart from these forces, the other force that can act is a body force, which typically is a gravitational force. Okay. Now what is gravitational force? How is it defined? Let me say that gravitational force is defined by say vector, let me call this as vector as P, okay, a vector P, and defined as body force vector per unit volume. So in other words, the force vector, these are all vectors, so the body force vector is defined as P into volume of the body, which can be said or which can be determined as delta S into H divided by 3. 1/3 delta H into S gives me the volume of the body. So this is the body force vector. Is that clear? That is a body force vector. So sigma of F is equal to 0. What does it mean? It means that this T plus this T, that is TE1 plus TE2 plus TE3 plus Tn plus that is equal to 0. All the sigma of F or sigma of all the forces are equal to 0. Okay? So that is what is meant by the equilibrium of forces. Let's just wait a minute, we will write that, and before that let us make a small approximation so that we need not write it again and again. What is that approximation? We said it's not an approximation, actually we remove that h tends to 0. What is that force which will be affected by h tending to 0? Body forces. So this will go to 0 when I put h is equal to 0. Right? Is that clear? Now let me express then Tn in terms of other 3 forces. Okay? The directions are taken care of, let us not worry about that. Okay, we know that directions are taken care of, or T of n, okay, into what? This is stress, so this is the stress vector, okay, that multiplied by area delta S is equal to T E1 into, what is delta S1? What is delta S1? N1 delta S, correct. So into N1 delta S plus, what is that next term? T E2 into N2 delta S plus T E3 into N3 into delta S. So this equation is the equilibrium, it depicts the equilibrium of this small tetrahedron which I have taken, okay, to bring in my stress tensor. Immediately the trick is out of the bag. What is that you are going to do now? What will you do now here? Yes, that's it. So you resolve this in x1, x2 and x3 direction, right? So resolving this in the 3 directions, say for example in the first direction, what is that I will get? Say T1, okay, T1 n, and cancelling of course delta S throughout on left hand side and the right hand side. What is that I will get? T1 n is equal to T1 E1 into N1 plus T2 E2 into N2 sorry E1 sorry E1 into N2 plus T3 E1 into no E2 E2 both of them are T1 T1 E2 and T1 E3. Yeah, that's good. So just in this, as we did in the previous one, same. There is no difference between the two. Is that clear? Okay. The same way you can write T2 and T3. Okay. Now before we go to the next one, let's rub this off. We'll have the result, okay, written in a slightly different notation. What is the notation we introduced for this? Sigma. So what is this? What is this? Sigma 1 1. What is this? Sigma 2 1. What is this? 3 1. Correct. Is that clear? Okay, hence I can write T1 of n as sigma 11 n1 plus what is the second term, sigma 21 n2 plus sigma 31 n3. Same way I can write T2 and T3. How will you write that? What will happen to this? N2 and so on, sigma 1, 2, N2 and so on. Now I'm quite lazy to write all this. So the first question you will ask is, how do I simplify this? I simplify this using what is called as an indical notation, by using indical notation. In indical notation, I will write, I'll explain that maybe in the next class. Let us write this first. In indical notation, I will write Ti is equal to sigma ji nj. Okay? In your earlier classes, you would have studied about summation convention. So you can say that summation from j is equal to 1 to 3. For example, when I is equal to 1, I get, using the summation convention, what is that I get? I get the equation which I have written here. Okay? So for example, from what you know already, you would have written this equation as T1 and 1 here. The next equation when I want to write, you would just replace this 1 by 2 and so on. Okay? In other words, by your summation convention, you would have written 3 equations. Einstein introduced a simple notation called indical notation, and he introduced a convention using this indical notation. This convention is called as Einstein convention. I'm not sure whether really Einstein introduced it, but the convention goes by Einstein's name. Okay? And under that convention, okay, we don't write down the summation, but we put certain rules for summation. As you see it, you immediately see one thing. There is a term here with repeated index. Index is repeated, j is repeated in that particular group or assembly. And I appears on the left hand side and right hand side. In other words, the index, some index are repeated and some index are free. We will learn more about these two indices in the next class. What these indices mean and how you use summation convention, we will see that in the next class.